Hi everyone, in the next couple of videos I'm going to show you that these arrows cannot be reversed. So we had this theorem, almost sure implies improbability convergence, LP also implies improbability convergence implies weak convergence, and so in the next couple of examples I show that the arrows cannot be reversed. In the first example I'm going to show you a convergence sequence in probability which will not be convergent almost surely. Let's see how that can be achieved. I'm going to draw a picture. Instead of a formal definition, I'm going to define random variables via a picture. The starting point is going to be a u, random variable u, that is uniform on the interval 0, 1. And all my other random variables will be functions of this u. So my first random variable, x1, will be a function of u. x1 will be the following function of u. If I plot u on this axis and put 1 here, then x1 will be 0 between 1 between 0 and 1/2. So x1, the function x1, will look like this. It's going to be 1 between 0 and 1/2 and 0 thereafter. So that's x1. If you want to formalize it, you can see the PDF notes. It's a little bit more formal there, but I'm just going to draw a picture here. So what is x2? x2 is going to be 0 when u is between 0 and 1/2. And it's going to be 1 when u is between 1/2 and 1. And I'm not going to tell you what these variables do at 1/2 and at 1. These are zero probability events, so I won't bother. And that's the first two. Now let me define the next three in a similar way. Again, here is u, here is 0, and here is 1. And here is 1/3 and 2/3. And so I'm going to define x3 again as a function of u. It's going to be 1 when u is between 0 and 1/3, and it's going to be 0 elsewhere. So that's x3, again a function of u. x4 is 1 between 1/3 and 2/3 for u. So that's x4. And then x5 is 1 when u is above 2/3. x5 is 1 here when u is between 2/3 and 1. That's x5. And now everybody gets the pattern, right? So x6 will be 1 when u is between 0 and 1/4. x7 is 1 when u is between 1/4 and 2/4, and so on and so on. Now what can I say about these random variables? The first question I want to ask is whether they converge in LP. So is it true that x and go to somewhere in LP? And what is the obvious candidate for a limit of the x random variables? Well, these are ones on a shorter and shorter interval. So for example, their expectations are smaller and smaller. So the natural candidate to convergence anywhere is of course 0. And to check that, what I want to see for LP convergence is to look at the expectation of my ith random variable, nth random variable, minus the suspected limit 0 to the p power. What is this? Now actually it turns out that it's very simple. Let's plug in n equals to 1. What is x1? x1 is 0 or 1. In fact, all the xn's are 0 or 1. x1 is 0 or 1. When x1 is 0, then I have 0 under the expectation. When x1 is 1, then I have 1 minus 0 to the p is 1 under the expectation. So it's 1 times the probability x1, which is from here 1/2. U is uniform between 0 and 1. x1 is 1 on an interval of half length. So this for n equals to 1, I get 1/2. The expectation for n equals to 2 is also 1/2. The expectation for n equals to 3, how can x3 minus 0 to the p power be 1? It's 1 when u is between 0 and 1/3, which is 1/3. And then the same happens for x4 and x5. So these are all 1/3. So expectation of x5 minus 0 to the p, it's still 1/3. What is the similar expression for x6? x6 would be 1 on the interval 0 to 1/4 and 0 elsewhere. So for x6 this is 1/4, and for x6, x7, x8 and x9 it's 1/4. The next 5 have 1/5 and the next 6 have 1/6, and so on and so on. You can easily see from here that the expectation of xn in general minus 0 to the p converges as n goes to infinity to 0, and therefore we do have LP convergence. So this sequence of random variables converges in LP to 0. If they converge in LP to 0, then they also converge in probability to 0 and weakly to 0. So we have improbability convergence as well. Xn converges to 0 in probability. Homework, check this directly from the definition of improbability convergence. It's not difficult. But if you look at any realization of u, actually probability 1 u is not a rational number, so it's not going to be in any of these division points for any n. If u is somewhere in here, then there will always be a random variable x which is equal to 0. So if u is, say, a little bit above 1/2 in some irrational point, then x1 is 0, but x2 is 1, x3 is 0, x4 is 1, x5 is 0. Then maybe x6 and x7 are 0, but x8 is again 1, x9 is 0, and so on and so on. Whenever u is not a rational point, which is probability 1, then we find that the xi's will be 1 infinitely often. But xn, let's use n, is 1 infinitely often. In other words, for infinitely many indices n, xn is 1 almost surely. So with the probability 1 event, u is not rational. In that case, there is always a later index n, so that xn is 1, which means that this sequence xn cannot converge to 0 almost surely. Of course, it cannot converge to anywhere else either. And therefore, we found an example which converges in LP, it converges in probability, it converges in weakly to 0, but it does not converge almost surely to 0. So this implication is not true.